So, in this resource, we're going to talk about how the myRIO does timer interrupts. And it's very similar to how it does digital input interrupts. So a lot of this will look familiar to you from before. So initializing the timer interrupt is similar. Yeah, there we go. We will use a separate thread to produce interrupts at periodic intervals. Within main, we will configure the timer interrupt and create a new thread to respond when the interrupt occurs. The two threads communicate through a globally defined thread resource structure, just like before. And so you do that in a very similar way. The IRQ type def struct thread resource.
Professor, I
Yeah.
have a question about the context. So
Sure.
what does it mean in the real world? Is context is just history, or
For a timer interrupt?
yeah, for this one?
Do you mean like in general, when would you need to use a timer interrupt, or?
No, what is the context? Because this one we use the IRQ context.
Okay.
One element of this.
IRQ
Right,
context
this one?
reserved.
Yeah.
Got you. So IRQ context is the it's I don't know if I have a good answer that sheds any light. It's essentially, you could think of it as like giving a name to the IRQ that you're using, I guess. I mean, context is not super descriptive, but approximately to figure out which IRQ you're using, this is the variable that's being used, I guess.
So the type of IRQ, just
Yeah.
the type.
Yeah, so you can do multiple IRQs, and this is how you would define which IRQ, I guess. That would be, it's associated with the number, the IRQ number, but not exactly the same. So, yeah. I hope that's somewhat satisfying. Yeah, sorry. Don't have a better answer for you. So NI provides C functions to set up timer interrupt requests, IRQs. Register the timer IRQ. The first of these functions reserves the interrupt from the FPGA and configures the timer and IRQ. Its prototype is IRQ register timer IRQ. So IRQ channel, IRQ context, and timeout are the three arguments, and we'll expand on each of these. So IRQ channel, the first of them, is a pointer to a structure containing the registers and settings of the IRQ I/O to modify, which are defined in the IRQ or the timer IRQ header file as being this. So the internal register, the setting register, and the timer I/O supported, the timer IRQ supported I/O, the timer channel. So that's how it's defined in timer IRQ. So you have to hand it an IRQ channel that is of this type, otherwise it will give you a problem. IRQ context is a pointer to a context variable identifying the interrupt to be reserved. It is the first component of the thread resources structure. So that's one way to think of it. And timeout is the timeout interval in microseconds. The return value is 0 for success. So the timeout interval is sort of the way to set how long it takes to do this interrupt. So it sets your BTI. Okay, so to create the thread interrupt, a new thread must be configured to service the timer interrupt. In main, we will use pthread create, just like we did before, to set up that thread. Its prototype is this, which looks, I believe, identical to the previous one. Remember there was this weird way of defining it? Yeah, so you're passing a function to a function, and then you're going to pass also the argument that you want that function to get to pthread create. It's weird, but and remember that this third argument is the interrupt service routine that you're going to write. So that's the function you hand it. So everything there is the same as before, and if a function also returns 0 for success. So we'll get a little bit more specific in this one. We can combine these ideas into a portion of the main code needed to initialize the timer IRQ. For interrupts triggered by the timer in the FPGA, we have this. So this is like, once again, sort of like the start of the code for you. So you want in your main to just sort of set this up. You got to set up the thread. You got to initialize the AIO, and this is how you set up the timer IRQ. This is how you start. But this isn't, of course, the whole thing you want to do in your main. But this is the part that has to do with the timer interrupt. Other main tasks would go after this. So if you need to do anything else in there are a couple other little things we would need. After the tasks of main are completed, it should signal the new thread to terminate by setting the IRQ thread ready flag in the thread resource structure. Then it should wait for the thread to terminate. For example, just like before, you set IRQ thread 0.thread IRQ thread ready to NFPGA false, and then you read status, and finally, the timer interrupt must be unregistered then. So unregister the timer interrupt using the same arguments from above. So IRQ timer 0 and IRQ thread 0 are from above. So it's the same arguments there. So this is like giving you like the beginning and the end of your mains, and you got to put a little bit in there in between, just like before. The interrupt thread. So the main stuff is like kind of like I want to say bookkeeping, administrative stuff in main. And you are going to also remember what we're doing in main besides doing the setting everything up is we're waiting for that backspace character. So you're waiting for the backspace character. When you see that backspace character, then you have to terminate the IRQ thread. So the interrupt thread. So this is the separate thread that was named and started by pthread create. Its overall task is to perform any necessary function in response to the interrupt. This thread will run until signaled to stop by main. The new thread is the starting routine specified in the pthread create function called in main. In our case, void timer IRQ thread void resource. So that's the sort of strange way of putting the function into pthread create, right? The first step in the timer IRQ thread is to cast its input argument passed as a pointer, a void pointer, into appropriate form. In our case, we cast the resource argument back to a thread resource structure, for example, this. And this is, once again, we did this in the last one as well. So the DI interrupt is almost identical for all this. The second step is to enter a while loop. So two functions are performed each time through the loop, as described in algorithm 4. So ISR thread loop pseudocode. While the main thread has not signaled this thread to stop, do this. So you're going to keep doing this loop over and over again until the main loop, which is looking for that, tells you to stop. So do this. Wait for the occurrence of the IRQ. So remember that our IRQ wait function times out though, right? So like we can't just wait for it forever. It's going to time out. So depending on how long that IRQ, the timer IRQ is set, it might time out. So we want to have that as one of our cases potentially to handle. Wait for the occurrence or timeout of the IRQ. Schedule the next interrupt. So that's the next thing we need to do. If the timer IRQ has been asserted, then perform operations to service the interrupt. So if the timer IRQ has been asserted, which means it didn't time out. So we're going to be doing this pretty fast, so we don't really think this is going to time out. But if we changed, it would suck if we didn't write that into our code to be able to handle it if it was timing out. That would be really hard to catch that bug. So it's best to just have it in there from the beginning so you don't forget that the wait can time out. So if the timer IRQ has been asserted, then perform operations to service the interrupt, and then acknowledge the interrupt, and then end the while loop. So we'll keep doing that over and over again. So in our case, typically what's going to happen is it's going to wait for 5, well, not quite 5 tenths of a millisecond, I guess. Half a millisecond. It's not going to sit there and wait for half a millisecond, though. It's not going to be like our old wait function. It's going to wait for the rest of the half a millisecond that's left over after it did the last operations, which were to compute the cascade function and to output. So read the input, compute the cascade function, and assert an output. That's going to take some time. So when it gets back to that IRQ wait at the top of the next loop, it's not going to have to wait a full half millisecond. It's going to wait less than that. And then it'll move on and compute it again. So it won't be just a fixed amount of time waiting at that IRQ wait. It's just going to wait there until it gets that thread back. Sorry?
Will it stop waiting because when we run it all the time?
It shouldn't stop. It should keep going. Yeah.
It's just less and less by certain amount of delay.
Well, so it'll wait, right? So as long as we don't overfill our time. So it's pretty much like, you could think of it as, this is one analogy. It tosses a ball up in the air, and it goes and does some stuff, and it comes back and it waits for the ball to come back down. And then it catches the ball, and it tosses it back up, and it runs and it does some other stuff, and it comes back and it waits until the ball comes back down. If you toss the ball up in the air and you go off and do stuff for too long, you're going to miss the ball coming back down, right? That's what you want to avoid. You don't want to have that happen. You can't get ahead though. Like, so if you throw the ball up in the air and like you do something really quick and you come back, like you're going to get back on cadence because you're going to wait until that ball drops. You're not going to like go grab the ball. You're going to wait till the ball drops each time. So you got to wait each time. The one thing you got to worry about is taking too much time in your ISR so that you don't overfill your time. So what happens, so in this case, the ball analogy doesn't work. If you miss it when you come back, you drop the ball. In the ISR loop, you will your wait function. So if you missed it, you're going to essentially wait an extra however long until the thing returns again. So it's going to keep returning, but if you miss it, actually, that's a good question. I don't know if this thing will do it. I don't actually know, because there are two different modes that it can. I don't know which mode it would do. You just don't ever want to do it, but if you do miss it, there's one of two options. Sometimes it won't return anything else, so you're just gonna be waiting forever. So it could be like the ball you threw up in the air. Or another possibility, which happens, and I don't remember if which one this one does. It might just come back around the next time. So like you get it the next time around, but you missed the one you were trying to get to. So your timing will be off by it. If you miss 1 by a factor of 2, if you miss 2 by a factor of 3. So I guess not by a factor of 3, by a factor of 1/2. So you're yeah. Well, no, by a factor of 3. So if you're missing them, that's bad, and you just want to avoid missing them.
Because the
So
IRQ
would it be pretty obvious that you're missing them?
It would be, because if you're looking at, like, say you're just passing the value through, you read it and then you write it, and you're missing them. And you could even do this. You could put in like your wait function in there or something like that, and like and intentionally miss it, or do a little like for loop in there that just takes a while. Like have it add 2 numbers together like 1,000 times or something, and then like make it miss. It's either going to be slower than you're anticipating, so the time lag is going to be greater, or you're going to have so that would be a time lag greater, means that it will keep returning. But if it's a ball toss up in the air and you don't catch it and then it's done, it'll just have a constant output. It'll just flatline wherever you end it. So that's a good question. I'm kind of curious which one it is.
Yeah. Because the IRQ wait will wait only 100 milliseconds.
IRQ wait. I think it is 100. Is it 100 milliseconds this timeout?
Yeah.
So yeah. So it would just end. I don't know if it'll set the output. I don't think it automatically sets the outputs to 0.
If we put the wait function for like several wait function, it will just delay it until the second time it's interrupt. It will just delay again. So it will be late for that.
Right. Yeah. If it times out, that's yeah.
If it times out, it will just send a signal to stop receiving the interrupt.
But it wouldn't. So the IRQ wait. Yeah. So it would. So say it doesn't return it. Say it's just like the ball you dropped, and if you miss it, you miss it. Then the IRQ wait on the next time would just be waiting until it timed out, and then it would go back through the loop, and it would wait until it timed out, and then it would wait until it timed out, and it would just continue waiting until it timed out.
Meeting.
Yeah, no meeting. Although that's a good question. Actually, I think that what it would do, it would wait till it timed out, and then it would toss another ball up in the air, and then it would miss it, and then it would wait till it timed out. So essentially, your rate would then be 100 milliseconds. It would be your IRQ wait. It would be your IRQ wait timeout. So, yeah. So I guess if that is the case, as long as you keep tossing a new ball up in the air, you're going to end up, your wait would be 100 milliseconds. That would be the delay. So, cool. So yeah, so that's the idea. You guys clearly understand this pretty well. That's good. So the while loop should continue until the IRQ thread ready flag set in main indicates the thread should end. For example, use the IRQ wait function to pause the loop while waiting for the interrupt. For our case, the call might be with timerIrq number as a constant, defining the timerIrq's IRQ number, defined in timerIrq.h. I know, it's a lot. do this. So IRQ wait, just like before, but now instead of using the, I forget the DI IRQ number, now it's the timer IRQ number. Notice that it receives the thread resource context and timer IRQ number information and returns the IRQ thread ready flag set in the main thread. Schedule the next interrupt by writing the time interval into the IRQ timerIrq register and set the IRQ timer set time flag. So this is back in the lab exercise, Dane, when you asked where are these coming from? So these are the values that, so they are in the header file, and we use them right here in this IRQ timer write and IRQ timer set time. So this is just to send it a true to the register, and this is to tell it how long to go. So this is going to be our 0.5 milliseconds. Until the next interrupt. So you set it in microseconds, so 500 microseconds, right? The myrio session used in these functions should be declared within this timer thread. That is, make sure that you have this at the top of your interrupt service routine. You needed all of this in the last one, so what I would do, if I were you guys, is potentially start with your interrupt service routine from before, and then change the parts that need changing, which aren't that many. I mean, this part needs changed, like that's the same. You need to change your IRQ wait to have this instead. So like, there are a few places you have to change things, but you already have code written for doing an interrupt, and they're very, very similar. So I would say start there maybe. And then here's the other part you're going to have to change. So because the IRQ wait times out after 100 milliseconds, we must check the IRQ assert flag to see if the timer IRQ has been asserted. In addition, after the interrupt is serviced, it must be acknowledged to the scheduler. For example, remember we used this the bit mask to see if that bit had been flipped. That's what we're doing here. So IRQ assert, you do the AND bit mask with a left shift by timer IRQ number. So bit leftwise, a left bitwise shift. Bit shift. Yeah. And then you bit mask it. And then you put in your interrupt service code here. So this is where, so this is like, the interrupt came in, now what do we do? And this is where you put like your analog input read.
I got you.
Yeah. And then you put your cascade. You gotta compute what the output should be. And then you got your analog output right. And then return. And then you got to do the acknowledge at the end of this too. So it's all very similar to before, but instead of it waiting for a button, this time it's waiting for a timed interruption to happen. And then you got to exit the pthread and return null. So that is how you do a timed interrupt. And this is just a better way to do timing than the wait functions that we've used before. Because you can predict how long it takes to throw the ball up in the air and then have it come back down. If you keep tossing the ball up in the air and then running and doing things and then coming back, as long as you get back in time to catch the ball, you know what your timing is. So that's the preferred way. The wait the wait function, we used that. It's a way to do timing, and it's not always bad to use it to do it that way, but it's not ideal, especially if what you need to do in the meantime is long compared to the BTI. So if it's much shorter than the BTI, then you're fine because it's like some small fraction. You're off a little bit, but not that much. The other time so you can get around that by timing or estimating how much time your other tasks take you, right? So you can do that. But where you run into trouble is if the amount of time that each task takes is variable. So like in the case of the speed function, when you hit the button and it prints to the screen, that takes longer than the other loop did. It's like printing to the screen took longer. So if your timing gets screwed up, then like not every BTI is actually the same. And so that's where the wait function has a lot of limitations. So this is definitely a better way to do most things, but sometimes you can get away with doing just a simple wait function.
So we're using Cascade then within the ISR function that we're writing.
Yeah. So it's not in main. It's going to be, Cascade's going to be to calculate what those A's and B's, well, no, it's going to be to calculate what Y is right now based on the A's and B's, based on past values of X and Y.
So we're writing three functions: main, Cascade, and then ISR.
Yep. Mm-hmm.
For this decrease my filter, and these numbers are coming from by default, or go back to this.
Yeah, are you talking about this one?
Yeah.
So this is given to you. I'll show you how to get them in one of these lectures. It's not bad getting these numbers from the transfer function, but so I'll show you the process of going to this from this. And so I'll show you that process, but it's not terrible to go through that. And you can use MATLAB to do that for you. So you give it this, and as long as you know what to tell MATLAB to do, it'll give you all of those coefficients. So the biquad coefficients, which is pretty sweet. Yeah. Oh, it's really cool. I am, there's so much cool stuff in this class. It's like, it's so hard to fit it all in, all of the fun. So much fun in one class.
Yeah. When I read through this interrupt handling, like there are many methods of handling interrupt, like nested. What we are doing is non-nested, simple one. And the other one is like nested and re-entrant. And the other one is the other prioritized interrupt, something like this. Which is way more complicated.
Yeah, it's pretty, we're just sticking to
Yeah.
pretty basic
Yeah.
building blocks. And then you can get really complicated really fast. But you can do pretty amazing stuff with just the simple building blocks. If you can measure analog inputs and you can write analog outputs and you can compute filter or controller outputs, digitized versions of a continuous one easily, then yeah, it essentially allows us to go from a theoretical like controller to an actual controller, which is what we'll do. And we're going to use this to build controllers in Lab 7 and 8. So we'll be able to, in MATLAB, design a controller, and then we'll be able to dump that to like the coefficients, and we'll even have it write those We don't have to type them in ourselves. And then we'll run the controller. So like we'll like go all the way from like the analysis to the implementation pretty seamlessly. So it's pretty cool. I've not seen a tool that costs less than 40 grand that can do that. There is this thing called a speed goat that takes a MATLAB controller and will implement it in real time in hardware for you. It's pretty cool. But yeah, like 40 grand or something like that. Like that was the one that I saw. I don't know if they're all that expensive, but essentially they're very expensive. So, and also it's not in an environment where it's like the speed goat thing is like a black box, and you wouldn't want to like put a speed goat in an actual piece of hardware you're designing. Like, yes, well, we'll have a $40,000 component, and then you would want to have it be an embedded computer that's on board. So actually doing like design on an embedded computer and implementing it and testing it, it's pretty cool to be able to do that whole process without too much trouble. So you could like tweak your controller, and then when you like design the final product, you like ship it with certain coefficients or whatever. But you could work on tweaking those coefficients pretty quickly using the methods that we'll learn. So it's pretty cool. I have to say, it's a pretty cool system. I can't take credit for it at all. I inherited it. So yeah, but the professor who developed the material originally, he said, well, it only took me like 30 years. So it took him a while. It shows. There's a lot to it.
You mean Professor Garbini?
Yeah, Professor Garbini. Yeah, UW. Thanks, Professor Garbini.